Hey everybody, Mr. Brooks here again. So today we're going to go over 11.5, which is alternating series. So for this, for all the convergence tests that we've been studying so far, so the limit comparison test, the direct comparison test, the integral test, we've been forced to only deal with functions, or sorry, series that have positive terms. So the alternating series, we actually finally get to tackle some with both positive and negative terms. So everything else has been limited so far, so this at least opens the door to have those negative terms. All right, so what is an alternating series? So an alternating series is a series, go figure, whose terms are alternating or alternately positive and negative. All right, so that's very straightforward. So an example here would give us, so if I had 1, negative 1/2, plus 1/3, minus 1/4, plus 1/5, minus so on. This is actually an example of the alternating harmonic series. Which is of the form -1 to the n minus 1, and then times 1 over n. So again, this is the alternating harmonic series. All right. Another one that we could see, so then that way we could say that it doesn't always have to start with a positive. We could have -1/2 plus 2/3 minus 3/4 plus 4/5 minus 5/6 plus so on. And this is actually the series as in goes from 1 to infinity of -1 to the n, n divided by n plus 1. All right, so again, so we finally get to deal with negative values, except for this we have to be very specific on our prescribed series here, so we have to be alternating between positive and negative values. All right, one important note to have here is that the nth term of an alternating series is of the form a sub n, which is equal to -1 to the n minus 1 times b sub n, and we're going to talk about what that b sub n is here in a second, or a sub n is equal to -1 to the n b sub n. So what this is saying is if we choose any random term out there, it's either going to be of the form -1 to the n minus 1 or -1 to the n term. So it's going to be positive or negative. Here, the b sub n, what that is representing is the number value itself. So where b sub n is a positive number. So in this case, it would be taking the absolute value of a sub n is equal to b sub n. So if we look back at our two examples, if I chose the second term in this first series, it's -1 to the n minus 1 because we have a negative value, and then the b sub n is 1/2 for that case. All right. So that's all that means in there. So this way you're used to seeing this because we are going to be using this idea of b sub n in our definitions, and so b sub n is the number itself, not, and so it's an absolute value of the term. All right. So this leads us into, well, how do we figure out if these guys converge or diverge? Okay, so this leads us into the alternating series test. Or for short, just like what we've done before, this is the AST. Okay, so the alternating series test. So here we're going to let B sub n, which is the thing that we just talked about, it's going to be greater than 0. So what we're doing here is saying it's going to be positive. Okay. The alternating series, which is the summation as n goes from 1 to infinity of -1 to the n minus 1. Now this can be slightly different. Here we're setting this up so that way when we talk about a proof of this particular test, we don't have to worry about generalization. We're still going to generalize it, but if we started with a negative, that's fine too. Our proof just goes a little bit differently, but this is just the setup. So this would look like B1 minus B2 plus B3 minus B4 and so on. So that's what it would look like. This converges if the following conditions are met. That's the cool part about this one, is the only thing that's required is that first it has to be an alternating series and B sub n has to be positive. So that's the only two things that we need to satisfy before we apply the test. Unlike the integral test where we had to have a positive continuous decreasing function to represent the series, or the limit comparison test or the direct comparison test, where with the limit comparison test we had to have both terms are positive. With the direct comparison test we had to have both are positive and one is smaller than the other. So we had a lot of conditions to meet. So this one's just very straightforward. If we have an alternating series, we're pretty much ready to start the test. Okay, so here are the two conditions. So condition 1 is that the limit as n approaches infinity of B sub n is equal to 0. Okay, so that's the nice thing here is we look at what's happening with that term, and is it going to be going to 0. So think about what that means. That's applying that idea of convergence for a series. So if a series converges, its limit is equal to 0. So this is satisfying that part to it. Now remember though, the converse is not true. If the limit of the series is 0, that does not mean that the series converges, because the biggest one I go to, again, and you're going to hate me for this, but the biggest one that I go back to is the harmonic series, because its limit is equal to 0, but we know that the series diverges. All right, so, and condition number 2 that's required is that B sub n is greater than or equal to B sub n plus 1 for all n, meaning that we're talking about, and so I'm going to write this in a different color so then that way you have a note here, is that it's decreasing in value. All right. So that's our two conditions. If we can show that its limit is equal to 0 and we show that it's decreasing, then we can then say by the alternating series test the series converges. Okay. So the idea of this particular theorem is a very easy visualization. So the idea. All right. So say that we have our number line here. Okay. And I'm going to put 0 over here. There's a reason I'm doing 0, because we just said that B sub n is greater than 0, and also our B1 back up here where we defined our alternating series is positive. Okay, so that's our first step. So let's think about this. If it's decreasing in value, then our big step here is I'm going to add to 0 B1. right, for my very first term. Okay, so here, the sum of that series, so if I looked at a partial sum, okay, so think about partial sum. The partial sum is S1. And so here I'm just going to represent with dotted lines going up, so then that way we have a visualization going on. I'm this far away now of positive B1. Okay, so that's its first partial sum. So now what I'm going to do is then I'm going to subtract, and I probably should have used red as the subtraction, but it's okay. All right, I'm going to subtract from B1, B2, which means my new sequence of partial sums is now smaller than the previous one. Okay, so I'm going to subtract a certain value away from there. So subtracting B2. And again, because we have decreasing values, B2 is less than B1, so we're not going to go back to 0, and we're not going to go past. Okay, so this is going to give us our new partial sum, S2. All right, well then I'm going to add to that B2, or sorry, B sub 3. Okay, well B sub 3 is smaller than B2, so therefore it's not going to go all the way back to B1 or S1. So then I have the new sequence of partial sums, S sub 3. And then I'm going to continue this. I'm going to subtract again B4. And so we get S4. And then I'm going to add again B sub 5. So we get S sub 5. And then I'm going to subtract again. So we're going to get S6. And so this alternating back and forth, what eventually is going to happen is we start going to approach some specific value. And this value is going to be the sum of the series. So notice that if we look at this, it looks like that the sequence of partial sums is now approaching some value S. So note here, the even partial sums, so S of 2n, are increasing, while the odd terms, the 2n minus 1, are decreasing. So it seems plausible that both are converging to some number S. And so that's the essence of the proof there. So it's a lot more mathematically rigorous, but here we're just going to go over such a generalization. So that way we can see from the picture that yes, it does look like we are approaching S, kind of using a limit process for that. All right. So now that we have that out of the way, now we can look at a bunch of examples, and then we're actually going to get into, can we approximate with this as well? Because we have this back and forth that's going on, eventually it looks like we can narrow down to where that sum is. And so that is something that we are going to investigate with this one. So this will be one of the few series that we can actually talk about estimating its value. All right, so determine if the following series converge or diverge. Okay, so again, when I write up a series, I want you guys to go ahead and try it out on your own. So once I have this one written, pause the video and then work this guy out on your own. All right, so we're going to try the alternating harmonic series and see what happens with this one. So go ahead and pause your video, and we're going to get started here in just a second. All right, so our solution. Okay, so first of all, is this an alternating series? Well, yes, so this 1 over n, that's always going to be positive. This negative 1 to the n plus 1 is going to be alternating in sign. So yes, this is a alternating series. So step 1, when we're applying this test, is we take the limit as n approaches infinity of 1 over n. Well, as n approaches infinity, the denominator increases to infinity, and so the overall fraction is going to go to 0. So yes, there's our check mark number 1 that we have. All right. Now the only other thing that we have to do is say, well, is this decreasing? All right, is b sub n greater than or equal to b sub n plus 1? All right. So in this case, b sub n is 1 over n. I'm going to put a question mark here. And the a sub n plus, or the b sub n plus 1 term is 1 over n plus 1. So wherever you see an n, replace it with n plus 1. All right. So if I look at this, yes, it is increasing. And another way that we could do that is go ahead and cross multiply. So we have n plus 1 is greater than or equal to, and I'm going to put a question mark above it, than n. Okay, is that true? Then yes, it is. But I'm going to go one step further and get a conclusion here. So I'm going to subtract n's from both sides. So I get, is 1 greater than or equal to 0? The answer is yes. So therefore, the series is decreasing. All right. And this is for all n values. All right. Since we don't have an n value here, this is true for all n. So therefore, the series, as n goes from 1 to infinity, of negative 1 to the n plus 1 of times 1 over n, converges by the AST, the alternating series test. And that's all you have to do. So that's it. All right. So let's look at another one. Number 2. All right. So check out the series here as n goes from 1 to infinity of n over negative 2 to the n minus 1. Okay. So pause the video, check it out, and see what you get. All right, so here's the solution. So first of all, this does not look like an alternating series at the very beginning, so we need to do a rewrite. Okay. So we have n over negative 2 to the n minus 1. This, to get my b sub n by itself, I'm going to pull out that negative. So that negative 1 was raised to the n minus 1. And then the rest of this is this n, and then 2 to the n minus 1. All right, so now that we have this b sub n by itself, we see that it is alternating, so we can apply the alternating series test. So number 1, we're going to get the limit as n approaches infinity of n over 2 to the n minus 1. Well, here, notice that both the numerator and the denominator both blow up to infinity. So I can't use L'Hopital's rule right off the bat yet, so I'm going to say let f of x equal x over 2 to the x minus 1. So then that way I have a function that represents it, and so then I can apply L'Hopital's rule to the function. All right, so as x approaches infinity, of x divided by 2 to the x minus 1. All right, we already concluded that both the numerator and denominator both go to infinity, so therefore we can apply L'Hopital's rule. So I use my LH here to indicate that I'm using that. And then I'm going to take the limit as x approaches infinity. All right, of 1 divided by 2 to the x minus 1, natural log of 2. All right. Well, as x approaches infinity, the numerator stays 1, the denominator blows up to infinity, so therefore this is equal to 0. All right, so that means that the limit as n approaches infinity of n over 2 to the n minus 1 is also equal to 0. Okay? So, part 2. Is b sub n greater than or equal to b sub n plus 1? So that's our question, right? So now that we satisfied our limit, and again, my suggestion for all of these when you're doing the alternating series, and we're going to see why here in a little bit, is always do the limit process first, because there's going to be some nice things that happen with that if we run into some issues, and we'll go over that example here in a second. All right, so our b sub n term is this n over 2 to the n minus 1 greater than or equal to, and I'm going to put a question mark, of n plus 1 divided by 2 to the n plus 1 minus 1, which is just n. All right, so here, this one's a little bit harder to tell, so what we're going to do is we're going to cross multiply. So I'm going to get n to the n greater than or equal to the n minus 1 times n plus 1. All right, I'm going to move everything over to one side. So I'm going to get this, and it doesn't matter which side that you move it to. So I'm going to move this one over to the right hand side. So I'm going to get n 2 to the n minus 2 to the n minus 1 times n plus 1. And I'm going to make this greater than or equal to 0. Again, I subtracted it all. I did not divide by a negative or multiply by a negative, so that kept everything in order for that part. Okay, so with that, let's multiply some values out here. So we have n 2 to the n minus 2 to the n minus 1, and it's multiplied by an n, minus 2 to the n minus 1, greater than or equal to 0. Notice that all three terms has a 2 to the n involved with it. So a 2 to the n minus 1, if I factor that out from it, I get n, so if I pull an n minus 1 out, that means there's still one copy left over, so I get a 2n minus n minus 1, greater than or equal to 0. All right, well, we know 2 to the n minus 1 can never equal 0, so that means I'm left with n minus 1 is greater than or equal to 0. Therefore, n has to be greater than or equal to 1. So notice, since our series starts at n is equal to 1, then this is true for all values of n. Therefore, we just satisfied that it is decreasing. So again, to kind of help validate as we go through, so if we go backwards, we're building up this inequality up at the top if we start as n is greater than or equal to 1. Okay, and likewise, as we move down, we can see the process that we did everything by either subtraction or anything like that. So we can see our validation going that way as well. So therefore, the series converges by the alternating series test. And that's it. And we're done with the problem. All right. So let's continue on. Let's look at a third example. So our third example is, and we're going to make this one a little bit more interesting, as n goes from 1 to infinity, negative 1 to the n plus 1, n plus 1, all divided by n. So if we looked at the terms, we'd get 2 over 1 minus 3 over 2 plus 4 over 3 minus 5 over 4, and so on. Okay, that 5 came out a little bit horrible, so we'll go ahead and fix that. All right, so step 1 for our solution is look at the limit. So I get the limit as n approaches infinity of n plus 1 over n. And look what happens. If I divide all the way through by n, again, this algebraic process, so that way we don't have to apply L'Hopital's rule, because I know you guys like to use L'Hopital's rule more than you need to. So we're going to get 1 plus 1 over n divided by 1. Well, that means the limit's equal to 1. Therefore, I cannot apply the alternating series test. Well, the alternating series test fails here, okay, because it does not satisfy the first condition. We can see that this is decreasing, so I am going to write this in here. B sub n is greater than or equal to b sub n plus 1. So that is true. However, since we don't satisfy the first condition, we cannot apply the alternating series test. Okay, so I'm going to put a note here. We cannot apply the alternating series test, okay, because it does not meet the first condition. Well, that means it's got to diverge then, right? And the answer is no. Okay. The reason for that is because the alternating series test, if we go back, and I am going to scroll up here, so give me a second. All right. It says converges if the following conditions are met. It does not say anything about diverges. So this has a similar fate as the test for divergence. The test for divergence, if we go through the process for the test for divergence and find out the limit is not equal to 0, then we can say that the series diverges. However, if it fails that part and it does equal 0, that does not mean that it converges. Same thing with alternating series test. If we cannot satisfy the conditions, both 1 and 2, of the alternating series test, it does not guarantee that the series diverges. Okay, but there is a little sliver of hope here. So one thing that we do get out of this is, however, we can use the test for divergence and say that the series diverges. Okay, so that's the cool part about this. So if we look at this, we'll notice that the limit is equal to 1. That means its limit was not going to equal 0 by the test for divergence. So this series diverges. Okay, so that's the nice thing. So if you are applying the alternating series test to this and condition 1 fails, more than likely the test for divergence can be applied and we can say that this series diverges. All right, so you got that, so let's deal with one more example. All right, and here's our series as n goes from 1 to infinity of -1 to the n, 3n, all divided by 4n minus 1. All right, so if we were to look at its terms, it would be -3 over 3 plus 6 over 7 minus 9 over 11, and so forth. All right, so if we're looking at that, so take a second, pause your video, try it out on your own. All right, so we're ready. So condition 1, is this an alternating series? Yes. This -1 to the n guarantees that it's alternating because this positive piece here, 3n over 4n minus 1, is always positive. So this is its alternating values, okay, or alternating signs. All right, so the limit as n approaches infinity of 3n over 4n minus 1, well, this is equal to the limit as n approaches infinity of 3 over 4 minus 1 over n, which is equal to 3/4. All right, this fails the alternating series test. However, the series diverges by the test for divergence. Okay, so that's the nice thing about this. Notice that I did not give the alternating series power test any power over this divergence piece here. We are strictly using the conclusion from the test divergence to talk about divergence. Okay, so the alternating series test does not help with that. It just led us to our conclusion, so that's all we have. All right, so that's how you deal with alternating series to determine if they converge or diverge. So the next thing is, as well, can we use these to approximate sums? Okay, because that's one thing since the geometric series that we've not been able to do. So estimating sums. All right, a partial sum, S of n, can be used to approximate the sum of a convergent series. Sorry, of a convergent. So if we know the series converges, then that should make sense that we can talk about partial sums as its approximation. However, this is not much use unless we know how accurate the approximation is. Okay, so I could have to go out before I start getting a more and more accurate reading on any convergent series, that I'd have to go out 100 terms in order to say, well, this is the approximate value. So there is a nice thing with alternating series because of this behavior of slicing back and forth that allows us to talk about the accuracy or the error in there. So this is leads into the alternating, and this one's a mouthful, series estimation theorem. So the alternating series estimation theorem. If S is equal to the sum of the alternating series that we introduced in our first theorem, okay, here B sub n is greater than 0. So if S is equal to the sum of the series, the sum so the alternating series satisfying, so this is talking about the series itself, one, that the limit as n approaches infinity of B sub n is equal to 0, and 2, B sub n plus 1 is less than B sub n. Okay, so notice here that in order to talk about this, we have to first use the alternating series test. So if it satisfies these two conditions, then, so here is the nice part about it, the absolute value of the remainder, which is equal to the absolute value of S minus S of n, so the sum minus its partial sum, is less than or equal to B sub n plus 1. Okay, and that's it. Here R sub n is the remainder, so what's left over. All right, so what we're saying is that the difference between the sum of the series and the nth partial sum is going to be less than or equal to the nth plus 1 term. So this leads us into our first problem. So I've got two good examples to go through this. All right. How many terms of the series do we need to add in order to find the sum of the series to an error, or absolute value of the error, of less than 0.00005. Okay? And to help with this calculation, 1 over 20,000. All right, so this is a very small error. Okay? In our series, that looks horrible. In our series is the following. -1, the n plus 1, divided by n to the 6th. Okay? So first of all, do we have an alternating series? The answer is yes. Okay? So first of all, part 1 is, does this series converge? So I'm going to take the limit as n approaches infinity of 1 over n to the 6th, and we know that this is equal to 0, so it satisfies the first condition. Condition number 2 is b sub n plus 1 less than or equal to b sub n. Okay, so we need to find out, does this decrease? So 1 over n plus 1 to the 6th, is that less than or equal to 1 over n to the 6th? All right, well, cross multiply, we get n to the 6th is less than or equal to n plus 1 to the 6th power. Okay, so there's a couple ways that we could do this. I could take the 6th root of this, and notice then I would get not 0. I would get n is less than or equal to n plus 1, 0 is less than or equal to 1. So yes, it does satisfy that. Another way that we could have done this is wrote out the 6th degree polynomial for this, subtracted the n is equal to 6, or the n to the 6th power. And what would have happened is this is all dealing with n is positive, and we'd have addition all the way through. So either way, you could solve this for that part. Okay, so by the AST, the series converges. Okay, which means now we can apply the alternating series estimation theorem. And just to help with that mouthful, if we say A set, that's what we're talking about. So the alternating series estimation theorem. All right, well, the alternating series estimation theorem says once that these are satisfied, then the remainder, which is equal to s minus s of n, is less than or equal to the nth plus 1 term. We want this term to be less than 0.05 because our error, notice, is a strict inequality here. Okay? Okay, so that's why we want this, so I'm going to put this in red, to be less than 0.00005. Again, that's where that strict inequality is coming from. Now, if I said less than or equal to, we could have equality here, and that's actually can change our answer. So we've got to be careful. All right, so our nth plus 1 term we found was 1 over n plus 1 to the 6th. We want this less than 1 over 20,000. All right, so what I can do, instead of cross multiplying, I can flip both sides and then flip the inequality around. So that's the same thing as n plus 1 to the 6th is greater than 20,000. And then I'm going to take the 6th root of both sides. So I get n plus 1 is greater than 5.2 approximately. Subtract the 1. So n has to be greater than 4.2. So that means in order to be less than this specific error of 0.00005, we need 5 terms. We need at least 5 terms because, remember, we had a strict inequality. We are going by integer values. So we need at least the first 5 terms. All right. So by the A set, n is equal to 5. All right. And so that is the end of that example. So again, the reason that we say n is equal to 5 is because, again, n has to be greater than 4.2, so the next integer value is 5. Now again, if we had equality here, we could say we'd still have to use 5 because we cannot be equal, an integer is not equal to 4.2, so we would have to use still at least 5 terms in that particular situation. All right. So another example that we can deal with is, once we've done that, is approximate the sum of the same series to 4 decimal places. Okay. So again, the series that we're looking at, as n goes from 1 to infinity, of -1 to the n plus 1 divided by n to the 6th. All right. We already know it satisfies the conditions of the alternating series test. So let's look at the terms here. All right. And I'm going to just write these out. 1 over 1 to the 6th minus 1 over 2 to the 6th plus 1 over 3 to the 6th minus 1 over 4 to the 6th, and so forth. Now I am going to a very specific region here in just a second. So there is a reason to my madness here to go out this far. All right. If I look at these terms, so this is where it gets a little bit more complicated in talking about calculations, especially if we had to do this in class, we would have to do this without a calculator. So luckily for you guys, you have calculators for your take-home test. So when you get to do this, I'm probably going to put something like this on the test. So this is a go ahead, a fair warning. All right. So what I'm going to do is I'm going to look at these values. Okay. If I add the first 9 terms, so if I look at the 9th partial sum, this is approximately 9.85552. All right. The nth plus 1 term would be b sub 10, which is equal to 0.000001. All right. If we subtract this term from 9, okay, then that does not change the 4th decimal place here. Okay. However, if we had subtracted, and I'm going to do the calculations real quick. So bear with me. So again, the reason here, if we added these guys up, this one does not affect the 4th decimal place when we subtracted the b sub n term. So let me write that. If we subtract b sub 10 from s sub 9, so again the ninth partial sum, this does not change the fourth decimal place. Okay, so by the A set, the alternating series estimation theorem, the sum of the series is correct to 4 decimal places. Point 856. So again, I did round that last value. So this is the approximation for it. So that's the cool thing about this is you would just look at the values and start looking at the partial sums and see which one is going to affect the fourth decimal place, and then that's the one that you go with. You go one step further than that one. So it takes 9 values to not start affecting the fourth decimal place. So then we use b sub 10 for that part. And that's all you have to do. So these guys are really just calculation heavy is what you have to look at. And a lot of them, just like this one, because we're dealing with 6 powers and stuff like that, that makes it more calculator based than anything. So what questions I do like is the previous example where you said, well, how many terms does it take to be within this error? So the second question is just an alternative to that. So this is similar to that error question as well. So again, from an algebraic and calculus standpoint, I do like the first example, and that's my hint to you guys. I do like the first example better than the second example. All right, so that finishes up the alternating series lecture. So next lecture is going to be the absolute convergence. So this 11.6 will end our introduction into series before we get into what we call power series and the Taylor and Maclaurin series later on. So this is what's going to be on the next test is 11.1 up to 11.7. 11.7 is talking about, okay, if we come across a particular series, what type of test do we do? So it's that strategy. And so we'll talk more about that at the end or in the next couple of lectures. All right. So make sure, again, going over your definitions. What is a series? What causes a series to converge? What are the tests that we have now? So we have the test for divergence. We have the integral test. We have the 2 comparison tests. We have the alternating series test. And also now we have the alternating series estimation theorem, which only works for alternating series. And then what are a couple of families of series that we know, which is the harmonic series, which is part of the P series, and then there's also the geometric series. So knowing the conditions of when those converge, when those diverge, those are highly important. All right, so again, go over those definitions. So repeat to yourself what those are. So then that way, when you're going through, especially 11.7, which is a great review section. So if you're like, I need some extra practice, there's a ton of examples in there to go through that you can walk through the process of saying, okay, I'm looking at this particular series, what do I need to apply? So that would be my suggestion for you guys to study. And then, yeah, I think you guys are going to do a great job. All right, so I'll see you next time. Have a wonderful day.